All right, we're back for part 2 of day 16, solving problems involving trig functions. So the idea here, before we get to our example, there's several ways to generate equations of models if we weren't given one. So we have some sort of situation that's periodic. It repeats itself in a regular way, a wheel going round or a pendulum going back and forth, or a record on a timetable, or somebody sitting on a Ferris wheel. Any sorts of these situations, a race car going around a track. Um, we can come up with a model if we're not given an equation. Last example, we were given an equation. We were just asked to answer questions about it. But what happens if we're asked to look at a situation and then come up with the equation? Well, there's three main ways. We could just do a bunch of measurements and then be able to write things like the amplitude and the period and the phase shift and the axis. So we just do a bunch of measurements in the situation and do that. And there's an example from the textbook there. We could collect data from the internet or from a book or whatever and look for key features. These key features again are the amplitude and the period and things like that allow us to write the equation. Another way, and we'll see this, is to use technology to generate a model. So for instance, we can just plunk all this data that we get from the internet into a graphing calculator, into a computer, and it'll spit out a model for us. Okay, and we'll see all of these three ways. So I've actually posted a video, and it's a little silly video of me demonstrating this lab. So the idea was there was a spring and a baseball, and I pulled it down a little bit and it started bouncing up and down, right? The idea is it could model a piston in an engine or a bungee jumper or something like that. And I'm just going to go through these three ways and come up with an equation for the same situation three different ways. So this is the ceiling here, and this is the ground, and there's the little CBR that I used in part 2. But for the measurements, right? And I took some of these measurements in the video, and now I'm just reporting. That was 125 centimeters off the ground, right? There was a tape measure next to that. That was around 125 centimeters. It got as close once the ball started bouncing up and down. I made these measurements, and this was I just eyeballed it when the ball was bouncing up and down. I read it off the tape measure. That got to be 107, and this is 143 as far as it got up. And in centimeters. I also, and you heard me count, and I can imagine how painful it was to hear me count those cycles. I counted as it was bouncing up and down how long it took to do 10. So 10 bounces was 19 seconds. Well, what does that mean per bounce? Because it's too hard to like, it only takes a very short amount of time for it to bounce once. Well, I just divide, right? So that's 1.9 seconds per bounce. And that's going to come in handy, because now if I wanted to write a trig function, what I wanted to do then is just fill in values for A, B, D, and C. That's based on this situation, right? Well, if I think about it, what's the amplitude? The amplitude is, this is the at rest, and we also call that the axis. And I also called it early on the resting point. Well, this application kind of makes sense that it's the resting point. If the ball was at rest, it's 125 centimeters. It's also the average height. When it's bouncing back and forth like this, it's 125 centimeters above the ground on average. So the axis is 125, and in fact, that's the C value, 125 centimeters goes there. But then the amplitude is this distance, right? Amplitude is just 143, subtract 125, which is 18 centimeters, about. the B value, well, the B value, I get that from the period, right? And we practiced that earlier in the lesson. So then the period was 1.9 seconds, but we know that that's also equal to the expression 160 over B. Cross multiply and divide, and I get a B value of about 189.5, about. Which is pretty crazy because we haven't seen a B value like that, but we haven't seen a period that was so short. The period was usually 360 degrees or 180 degrees or something like that. In the previous one, it was 12 months. Here it's 1.9 seconds. Fine and dandy. And that's about everything. The only weird thing is this D, right? What was the phase shift? Well, where did the ball start in its cycle? I wasn't even paying attention. And in fact, the the phase shift doesn't really matter. And I'm just gonna, I don't know where the ball was when I started counting or anything like that. I'm gonna let it be 0. Okay, just to make our model a little bit more simple, and plus it doesn't matter. If we would have started timing a little bit later, the D value would have changed a little bit. So we've got 18 sine 189.5 x minus 0. So I'm just going to put it in like that, and then plus 125. T seconds. I guess this x should be a t. I'll do that. And then the y is the distance, isn't it? It's the distance that it's above the ground. And this function will do it for you. All right, well, what's the next technique? The next technique up here was to collect data. And I showed you how I used the CBR, and I collected a bunch of data. Well, this is the data. Okay, I just took this from the CBR and then wrote it on there. Well, how do I make any sense of this stuff? Certainly I could plot it, I suppose, plot all these points and then try and find the amplitude and the minimum and maximum and all that business, the period. But remember, all I really need to graph something is the minimum and the maximum. And especially if it's a cos function. If it's a cos function, that'll even give me the phase shift, because remember, a cos function, if we're graphing a cos function, whatever this shift is here, that's the phase shift, because normally we start at a maximum. So if I just look in this table for a maximum, there it is there, and then I'm going to look for the next minimum right there, then those 2 points will essentially give me all the information. We did one like this a little bit earlier, but let's write down. I'm going to use a cos function this time just because of this minimum maximum business. So I got a cos bx minus d plus c equals b equals c equals d equals. Okay, notice, and then I'm going to draw a little sketch to help me find these. I know some of you don't need to do that, but I do. The maximum here, and there's the minimum. So this is at 0.6 seconds. It was at a maximum of 1.46 meters away from off the ground, or from the CBR. And over here at 1.5 seconds, it was at a minimum of 1.05, right? So I can see the minimum and maximum. Well, what can I do? How does that help me? Well, notice the axis, the D value is right in between them, right? So I'm going to go, the D value is 146 plus 105 divided by 2 gives me about, the C value. Oh, darn. Let me just move it. I wonder if I can do this. Aha, nice. And that's the C value. The D value is inside. That's the phase shift. And that is about 1.25. And notice that in our example earlier, the C value, the axis value was 125, but that was in centimeters, and this is in meters now because I got it from the calculator. So this is about 1.25 meters. And then what's the amplitude? The amplitude is that distance there, 146, 1.46, subtract 1.25 is about 0.21. Now we had it as 18 centimeters or something like that, but 21 centimeters is pretty close. The B value, or the D value, let's do the D value first. The D value is the phase shift. The phase shift, I've moved it that much to the right, right? Because the cosine starts at its maximum. The D value here is just 0.6. Easy this way, right? There's the maximum. It's a cos graph. That's the shift. What's left? Period. The period. Well, the period was, from maximum to minimum. That's only half a period, right? Because now it's going to go back up to its maximum over here somewhere, like that. Well, this distance is 1.5 subtract 0.6 is about 0.9. The period then will be twice that. 1.8. If I do a little calculations, I can find my B value. And notice our period when we did the measurements was 1.9, so it was pretty close. Here, ... B is about 200. And then I can write my function. And in this one, notice that everything's in meters. X is still in seconds, but the output Y, the distance is in meters. And so it's pretty close to our earlier values that we just measured. Like that's pretty close. That was pretty close. That was 0.21. And even our B value was pretty close. Now the last video that I did on the YouTube about this lab showed how to do regression. And regression, essentially, you put all the values into the table, and then you use the calculator, and you go stat, over to calc, and then you scroll down and choose sine reg, and then it clicks away like it showed in the video, and it came up with this equation. So the calculator gives you a sine equation. And this, I showed you this on the video. And this is in meters again. Notice some similarities. First of all, how close the amplitude is from our earlier ones. How, like the axis or resting point, the C value is dead on. The other two are way off. And one of the problems here is the graphing calculator does regression in radians, not in degrees. So you know how if you do some trig and your calculator isn't set on the right setting, it messes up? Well, you can't unmess this up. So this is a good model, except for it's in radians. This is in radians, and so it's nowhere near our B value from before. Similarly, the calculator gives us the phase shift, not with the double brackets. Notice that this would be the value of B times D here, and we could still figure out what the phase shift they're trying to tell us what it is, but you know, that's not quite the same as what we're used to. Now it's your turn, and notice you get lots of choice in these examples. Some of them, this is like example 1, and here is all the stuff that we did with the bouncing ball, except for it's going to be up to you now. All right, this is all make up your own model, either given some data or some measurements, or even given a graph, okay? So go at that.